When considering the stability of nuclei, it is important to look at the balance between protons and neutrons. And therefore this graph is very, very important. This is a graph that plots the number of neutrons versus the number of protons in specific nuclides or in nuclei. So on the vertical axis we have the number of neutrons, and on the horizontal axis we have the number of protons. So the number of protons is we know it as Z, or the atomic number, and the number of neutrons we are going to refer to as N. Now if you take all the isotopes that we know as humans and we plot them on this graph, then we get this region here of data, which you can see is very extensive. Now, when looking at those nuclei which are stable, then we get this region here, what we call the band of stability. Now, this has been determined experimentally by seeing how these particular nuclides, how stable or how unstable they are. These nuclides that are in this region, that are not on this band, are unstable, and so they will undergo nuclear processes where they will move toward the band of stability. And so this is what this module is about. It's about radioactive decay, the various methods of decay that will take isotopes or nuclides that are unstable and will take them toward this band of stability. We will be looking at this graph in great detail, and I would like to just refer to some terminology. We see this region here is made up of stable nuclei, and we refer to this as non-radioactive. In other words, they're not going to undergo nuclear processes because they are already stable. But these isotopes or nuclides, types of nuclei that are in this region, these are known as radioactive. Now with this straight line here, which is at 45 degrees from the horizontal and the vertical axis, this would be like a y equals x graph. This is where the number of neutrons equals the number of protons. And we'll see that with the very light nuclei, that the band of stability lies on this n equals z, which means that in these nuclei, the number of neutrons and the number of protons is the same. But as we get further along, or go further along here, where the number of protons is getting more, we see that in order to keep the nuclei stable, we need more neutrons than we need protons. And that has got to do with adding strong nuclear interaction in order to balance the electrostatic repulsion due to the protons in the nuclei. So looking closely at this graph, as has already been mentioned, we can see that for Z less than 20, in other words, isotopes where the atomic number, the number of protons, is less than 20, that we can approximate the line of stability or the band of stability with a linear function n approximately equal to z, or y equals to x. When we look at this graph, we can say that the isotopes, the radioactive isotopes that lie above the band of stability, this being the band of stability or the line of stability, that these isotopes are neutron-rich nuclides. By nuclide, it's specified, we're talking about a type of nucleus. So we're talking about the nucleus of a specific element or the nucleus of a specific isotope of an element. So I will use isotopes, nuclei, and nuclides interchangeably. So neutron-rich nuclides, where the ratio of neutrons to protons will be greater than 1, these will release neutrons to achieve stability. So what will happen is they will undergo radioactive processes where the neutrons will either be released from the nucleus or they will be converted into protons. The band of radioactive isotopes under the line of stability, these are what we refer to as proton-rich nuclides. This is where the neutron to proton ratio will be less than 1 because there will be more protons than neutrons. Or let's just say that there are too many protons in order for it to be stable. So we can see with heavier elements that here's where n equals z, this region here will still be defined as a proton-rich band, even though it sits above n equals z. And the reason why we'll say that is because here there are still too many protons for it to be stable, so it's going to need to increase the number of neutrons. So these release protons to achieve stability. So let's now define radioactive nuclides. These are unstable nuclei where the strong nuclear force does not provide a large enough binding energy to keep the nucleus intact. So what that means is that there's an instability between the electrostatic force of repulsion, which is caused by the protons. Remember, the neutrons are neutral, so they are not going to exercise electrostatic repulsion or attraction, but the protons are positive and like charges repel, so there's always this repulsion there. And so the neutrons that are added, they add strong nuclear interaction. Remember, strong nuclear interaction takes place between baryons, so that would be neutrons and protons, and so they would attract. Protons would also be attracted to each other, but at a very, very close range, and the electrostatic repulsion would act before the strong interaction acts, because the strong interaction range is very, very small, remember, of the order of 10 to the minus 15 meters, whereas the electrostatic repulsion acts over much larger distances. So the repulsion will occur before the actual the strong nuclear interaction will take place, and therefore it won't happen because the protons, if they're on their own, will not get close enough for the strong nuclear interaction to take place. And that's why neutrons need to be added, because they're not repelled by the protons and they add to the strong nuclear interaction. Let's talk about radioactivity and radioactive decay. They mean the same thing. This is the spontaneous emission of particles or high energy photons from unstable nuclei as they decay from higher energy to lower energy states. So firstly, the word spontaneous means that it is not initiated. This happens without artificial initiation. We will see that certain types of radioactive decay produce particles and others produce high energy photons. The key thing is, the driving force is that unstable nuclei move toward lower states, more stable nuclei. So the unstable nuclei are at a higher energy and the stable nuclei are at a lower energy, and that process involves either the conversion of neutrons to protons, protons to neutrons, or the emission, as you will see, of alpha particles, that we refer to as a decay. There is a change to something that is of a lower energy. There are three main types of radioactive decay. The first one we're going to look at is alpha decay, then we're going to look at beta decay, and then we're going to look at gamma decay. And alpha, beta, and gamma, they come from the Greek alphabet, a bit like A, B, C, and so these decay processes have been named in this way. So alpha decay is where there is an emission of a helium nucleus. Now, a helium nucleus, helium as an atom consists of 2 protons. That's why there's an atomic number of 2 and appears as the second element on the periodic table. It has 2 neutrons as well, so 2 protons plus 2 neutrons gives us 4 nucleons, so it's got a mass number of 4. But because it is only the nucleus, the 2 electrons in the first energy level are not there. And so therefore there's an imbalance in the protons and electrons. There are no electrons, so therefore it has a net +2 charge. We refer to the helium nucleus as alpha 4-2, so that's the alpha particle. The general equation is if you have a nucleus X, that's the element, and you have the mass number A and the atomic number Z, then when this alpha particle is physically emitted from the nucleus, as you can see here, then the nucleus that remains, what we refer to as the daughter nucleus, it is going to have a mass number that's less by 4 to the original mass number of the parent nucleus. And that's because the alpha particle has a mass number of 4 and is no longer in the nucleus. And because the alpha particle takes 2 protons with it, the atomic number of the daughter nucleus is 2 less than the atomic number of the parent nucleus. So we can see here that A becomes A minus 4 plus 4, and when you add those together it gives you the A, so there is a conservation there of the mass number. With alpha decay, we see that there's also a conservation of the atomic number, because Z minus 2 plus 2 gives us Z. So here's an example. So if we take the uranium-238 nucleus, it undergoes a decay event where now an alpha particle is emitted, and what is left behind is the parent nucleus has now become thorium. Why? Because in losing 2 protons, the uranium nucleus has now become a thorium nucleus, because thorium has an atomic number of 19. Remember, it's the atomic number that determines what type of element. And so this will be a thorium-24, sorry, not thorium-234 nucleus. And if we write this out as an equation, which you can be asked to do, we have U92238, which now, using this standard or general equation, becomes 92 minus 2, which is 90, and 238 minus 4 becomes 234. On your periodic table, you will pick it up as thorium. We will supply you with a periodic table in your tests and exams, and the alpha particle is 24. So if we ask you for the general equation of this alpha decay, that is what you would write down. So let's now look at the properties of alpha radiation. The alpha particle that is emitted is a helium nucleus. The charge is +2, and that means 2 multiplied by the electron charge, which is 1.6 times 10 to the negative 19 coulombs. But remember, electron charge is negative, so proton charge is positive. So it'll be plus 1.6 times 10 to the negative 19 coulombs. The mass of an alpha particle is 6.64 times 10 to the negative 27 kilograms. looking at the interaction, each alpha particle strips 2 electrons from the surrounding air particles to ionize the air. So about 100,000 ions per millimeter of air for 2 megaelectron volt alpha particles. So this is the interaction that the alpha particles undergo when they have left the nucleus. So alpha particles are able to ionize the substance through which they move, and the reason for that is because it's a positive helium nucleus, it's going to be very attractive to electrons in atoms in the medium surrounding the alpha particles as they are emitted. And so this is how alpha particles are detected, for instance, in bubble chambers and in ionization chambers, because as they move through the medium, they strip the electrons of the medium's atoms, and this can be picked up, for instance, in a bubble chamber. The range is approximately 5 centimeters. The penetration, it's not highly energetic, so it can actually be stopped. Alpha particles can be stopped by a piece of paper. They have very high ionizing ability, and they are detected in Geiger-Müller tubes, in cloud chambers, as I've referred to, in photographic paper. And they are affected by electric and magnetic fields because the alpha particle is positive. It can be affected by electric field because electric field affects positive and negative charges. Magnetic fields affect moving charges. You'll learn more about this in grade 12 in your standard grade 12 physics syllabus. They undergo something called a Lorentz force. So if you've got a charge that is moving in a magnetic field, it undergoes what was referred to as a Lorentz force. Let's now look at a worked example. So we have radon, which is a radioactive gas that decays by alpha emission to become polonium. The equation is that. Show that A, the mass number, and Z, the atomic number, are conserved. So I've rewritten the equation by using a color code. I've used red for the mass numbers, or the nucleon numbers, and I've used blue for the atomic numbers. The radon is the parent nucleus, the polonium is the daughter nucleus, and we know that the alpha particle is the helium-4 nucleus. Now, just something interesting, polonium comes from Poland, the word Poland, and the reason for that is Madame Curie, who was Polish, was one of the founders of the study of radioactivity, and she worked with radium, and she also worked with polonium, which eventually actually cost her her life, sadly. So now if we take the nucleon number A, the left-hand side is 222, the right-hand side is 218 plus 4, which is 222, which shows that the left-hand side equals the right-hand side, therefore the nucleon number or the mass number is conserved. Looking now at the atomic number, which equals Z, the left-hand side is 86, and the right-hand side is 84 plus 2 is 86, and therefore the left-hand side equals the right-hand side, and therefore the atomic number is conserved. So for alpha decay, the mass number or the nucleon number and the atomic number or the proton number is conserved.